All right, welcome. Today, we're going to crack open one of the most powerful and honestly most elegant tools in all of data science, Singular Value Decomposition, or SVD. You can think of it as a secret code that's hidden inside our data, one that reveals what truly matters. So where does this secret code even show up?
Okay, so get this. What could possibly connect Netflix telling you what movie to watch next, scientists processing genomic signals, and physicists trying to understand quantum mechanics? I know, it sounds like the setup for a really bad joke, but the answer is actually pretty profound.
The connection is a single mathematical tool. It's kind of like a master key that can unlock the most important patterns hidden inside pretty much any data set you can throw at it.
So let's dive into this data master key. What is it really, and why is it so ridiculously effective across so many completely different fields?
I mean, just look at this list. The sheer variety here is incredible. SVD is the engine behind recommender systems, figuring out these hidden connections between what you like and what you might like. It's the core of principal component analysis, which is just a fancy way of saying making complicated data simpler. And yeah, it's used in image compression, signal processing, and even for describing the weirdness of quantum entanglement. It is, no joke, everywhere.
Now, all of that sounds incredibly complex, right? But here's the crazy part. The genius of SVD is that, at its heart, it's actually just simple geometry. We're going to peel back all the intimidating math and just look at the core idea, which boils down to 3 simple actions.
And that's the secret sauce. Anytime you use a matrix to stretch or squish or twist your data, no matter how complicated that transformation seems, it can always be broken down into a sequence of 3 basic moves.
And here they are. Step 1, you rotate your data. Step 2, you stretch or squish that data along its new axes. And step 3, you just rotate it again. That's it. That's the whole thing. Rotation, scaling, rotation. Every complex transformation is just a combination of those 3 things.
And this quote right here, it just nails the visual. Imagine all your data points form a perfect sphere. When you apply one of these transformations, that sphere gets warped into an ellipsoid, like a stretched out ball. The SVD tells you exactly how that happens. The rotations line everything up, and these things called singular values tell you exactly how much to stretch along each direction to get that final shape.
Okay, so now that you've got that picture in your head, let's put the official name and formula to it. Any matrix, we'll call it M, can be broken down or factorized into 3 other matrices, U, sigma, and V transpose. This famous little equation is the mathematical blueprint for that whole rotation, scaling, rotation process we just walked through.
And let's break it down. It's really simple. The U and the V matrices, those are your singular vectors. All they do is handle the rotations. They line everything up. And that matrix in the middle, sigma, it's the best part. It's super simple. It only has numbers on the diagonal. These are your singular values, and they only do one thing, scale. They represent the pure stretch along those new axes.
All right, so a simple geometric idea, that's cool and all. But how does that actually translate into these super powerful real-world applications? Let's see how this simple concept builds into something incredibly useful.
Well, the real magic here comes from a principle called the Eckart-Young theorem. Now, what that basically says, and this is the important part, is that if you want the absolute best simplified version of your data, SVD is how you get it. By focusing only on the largest singular values, the biggest stretches, we can capture the absolute essence of our data and just throw away the noise.
And honestly, there's no better way to see this in action than with image compression. An image is really just a big grid, a matrix of pixel values. By using SVD, we can represent that whole matrix, not with every single pixel, but with just the most important singular values and their directions.
So, for example, if we decide to keep the top 100 singular values, the 100 biggest, most important stretches, we can rebuild the image and, well, look at that. It's almost perfect. We're using way less data, but we've captured pretty much all of the essential information. But now, check this out. Look what happens when we get really aggressive and use only the top 10. The image is definitely blurrier, but you can still totally tell what it is, right? We've thrown out most of the data, but the most dominant patterns, the real soul of the image, are still there. That is the power of approximation. Okay, so SVD is obviously a total pro when it comes to 2D data like an image.
But what happens when our data isn't flat? What about higher dimensions? This is where the core ideas of SVD have been taken to a whole new level.
So first, let's get a quick definition out of the way. We all know a matrix is a flat, 2D grid of numbers. Well, a tensor just generalizes that idea to more dimensions. So instead of a square of data, think of a cube of data, or even a hypercube that we can't really visualize. This is the kind of data you run into in quantum physics and advanced AI. So how on earth do you compress something that enormous? Well, you use a technique called a matrix product state, or a tensor train. It takes the exact same idea as SVD, breaking something big into smaller linked pieces, and just applies it to these massive tensors. It turns a giant, unwieldy hypercube of data into a simple chain of smaller connected tensors.
And this graph right here is where you really see the payoff. It's just staggering. Storing the full tensor means the amount of data you need grows exponentially. It gets impossibly big, incredibly fast. But the tensor train, it only grows linearly. The difference is almost unbelievable.
Just let that sink in for a second. We're going from exponential growth to linear growth. This isn't just a small improvement. This is the difference between a problem that would literally break our best supercomputers and one that's actually solvable. This leap is what makes working with the crazy high-dimensional data in quantum mechanics and cutting-edge AI even possible.
All right, so after all that, let's just pull back for a second and really nail down why this one mathematical tool is so fundamentally important across the board. At its core, SVD gives us the absolute best way to compress data while losing the least amount of crucial information. It automatically finds the most important patterns and directions buried in all the noise. It lets us take overwhelmingly complex problems and make them manageable. It helps solve tricky linear equations. And, as we just saw, it forms the foundation for even more powerful, advanced techniques.
Ultimately, SVD is a tool for finding what matters. It takes this messy, chaotic cloud of data and shows us the main directions, the principal axes, where the most important information really lives. And that kind of leaves us with one last big thought. If we can do this for data, what would it mean if we could find the fundamental axes our most complex problems in science or even in society? Hey, thanks for diving into this with me.